Hey,
Hey, what's up?
what's up? What's up? Thank you for being flexible.
Oh yeah, totally.
Um, yeah. So quite a bit I want to go over today. Um, if you want, we could start with that problem that it was like the EV problem with the photoelectric effect.
Uh-huh. Yeah. So let's see. Um, okay. Yeah, you sent me like a picture electron volts versus joules, but it's like super tiny. I couldn't really see it. But you said if you look at the bottom left, it explains it pretty simply. It's just that it's the image shows up really tiny for me. Yeah.
Do you see my screen?
Yeah.
Okay, hold on.
Yep.
So
Oh, it's
it's okay. It's still probably super blurry, but yeah. The resolution just sucks. But it basically says that the number of electrons equals the number of electron volts over the voltage.
uh-huh.
And so if you literally plug in um like that the numbers that we get into that quote unquote formula, you end up getting the answer. Uh yeah, here.
Uh-huh. Yeah. So let's talk. Yeah, okay. So basically, um, a volt is equivalent to joules per coulomb, right?
Yep.
And the charge of one electron is 1.6 times 10 to the negative 19 coulombs.
Yeah.
And so what an electron volt is the energy of an electron.
Mhm.
Okay. So
Yeah.
So that one electron volt is
You
going
said
to,
electron volt is what again? Like the what?
oh, it's the energy of a single electron.
Okay.
Yeah. And so uh, yeah, so basically yeah, so one electron volt is going to be equivalent to 1.6 times 10 to the negative 19 joules,
Mhm.
right? And and when we did the um, work function equation, we got a value of 2 electron volts, which would then be this amount. Yeah.
Yeah, just times two. So like 3.2. Yeah.
Okay. Now, okay. Now with the this thing here, right? It's yeah, I was spending a lot of time like trying to reconcile the denominator here and you know, and then like thinking about this entire spherical shell thing that like as it loses electrons becomes more positive and it can be treated as a point charge, which has, its own formula and all of that stuff, but like uh but we can we can kind of just we don't have to really worry about the denominator here because we have this value that includes the charge and the value on the top. So this is going to be, I just rounded it to 5 times 10 to the negative 8 volts. And if you remember, a volt is joules per coulomb, right? So this is the same thing as joules per coulomb, which
Hmm.
means to turn it into joules, I would multiply it by the number of like the charge in coulombs, right?
Hmm.
And so the charge in coulombs for a single electron is going to be the 1.6 E negative 19 coulombs per one electron, right?
Yeah.
And so this will give me the amount of energy in that one um, electron. And then to get the number of electrons, you're going to multiply it by your number of electrons, like here. And so what you're basically doing is, what you're basically doing is you're taking the um, voltage term and you're multiplying it by the charge of a single electron. And oh wait, I'm sorry. This is going to be, since it's 2 electron volts, this will have to be the 3.2. But yeah, so basically that's just what, how I did it, like just knowing that um like that the voltage could be, if you multiply the voltage by the charge of the electron and you multiply that by the number of electrons, you should be getting that energy value of the electron, which is the 2 electron volts, or 3.2 E negative 19 joules. And then we just rearrange to solve. So the N E here stands for the number of electrons. So to get the number of electrons, we divide the 3.2 times 10 to the negative 19 joules by 5 E negative 8, like joules per coulomb, aka volts, times uh, the charge per electron, which is 1.6 E negative 19 coulombs per electron. And then this is going to give us, like, the joules cancel, the coulombs cancel. We end up getting the answer in, number of electrons. And so that's pretty much it. Math here is kind of simple. This goes into this twice. So it's just 2 over 5, which is 0.4, times 10 to the 8th power, which when you rearrange turns into 4 times 10 to the 7th. So yeah, what you did is could also work, right? What I think you did was um, you did 2 electron volts divided by, what was it?
Yeah, 4.8.
Yeah. Um, point 4 E. Oh yeah. That works. But how are we gonna be able to come up with something like that? We have to recognize that an electron volt is the energy, not the voltage, but the energy um of an electron. And you know, 1 electron volt is 1.6 times 10 to the negative 19, and that cancels out. And so yeah, you can do it that way too, as long as you understand. Like, yeah, I guess the key takeaways here is just that um an electron volt is equal to the energy in joules of a single electron, and that's just going to be, it's essentially the same number as the charge in coulombs, but uh you know in joules.
Yeah. So like it's so I mean like this, I guess, would work.
Voltage times charge of electron times number of electrons equals energy of electrons in joules. Let's see. Okay, yeah. Yeah. And then, just make sure that you know that a volt is joules per coulomb.
Yeah, I have that. I already have that like implants in my head.
Yeah.
Yeah.
And then, yeah, and then also that an electron volt is not a type of volt.
Okay.
Like it's the energy of the electron.
So that 5 times 10 to negative 8, that's like this value. It's the volts of total electrons.
What are you saying? You're saying what?
The value, the 5 times 10 to negative 8, like the volts. How would you describe that?
Oh yeah, just the voltage, I guess, the of the sphere that is, having electrons leave. Um, like, yeah, when I was like trying to do this yesterday, like I was thinking, like of things like permittivity of like free space, like that's what that E naught term is, and there's like, because like the what is it? The voltage could be K Q over R, and the K is actually equal to the 1 over 4 pi E naught.
Okay.
Yeah, 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 yeah.
Uh,
Anyway, let
yeah, yeah. Anyway. Okay, but it's good. I mean, dimensional analysis honestly played a big part here, and that's like everywhere I read, that's like the number one thing for CP. So like,
oh yeah, yep, yep.
yeah. Okay, next is this whole passage.
All right. So, okay,
Let's start.
do your thing with your buzzwords and all that.
Yes, sir. Okay. DNA is compacted into nucleosomes with histones and eukaryotes. I mean, eukaryotes, we need to know the difference between those and prokaryotes.
What about,
Um,
yeah,
what's up? There's also, I guess, nucleosomes and histones, but like that's not very like I know that's buzzword material, but
it's not very what?
I don't know if it's buzzword material,
Oh,
buzzword worthy.
it's a trillion% buzzword material.
Okay.
Anytime you talk about expression, this is gonna like so yeah, so tell me about these, yeah.
Okay. Well, I know histones, that is what DNA is wrapped around, and Um, basically, when you have tight wrapping around the histones, the DNA is not expressed as much, and that's referred to as heterochromatin. That's the DNA is methylated. When it's unwrapped, it's being expressed, and so that there's acetylation going on. That's euchromatin.
Okay.
Uh, yeah, and I mean, they like to ask the questions about like lysine and positive negative charges or whatever.
Got it. So all right, so the histone is the thing that the DNA, like the beads on the string that the DNA wraps around, and the nucleosome is like like the unit of like DNA with the histones.
The nucleosome is the DNA and the histones together.
Yeah. You
Okay, okay.
have an octamer of the histones, meaning 8 histones, like per, what is it, nucleosome.
Okay. Um, do you know why this doesn't relate to this, but do you know why, like, in some other parts of chemistry, for example, like, um, octahedral,
Yeah.
it's six.
It's
There's
called
six
that
units, but
because
it's not eight.
there's six. Sorry, it's called that because there's 8 faces to the shape.
Oh, okay.
Because imagine
Uh,
imagine basically a pyramid, right? That you know uh is like this.
yeah.
Um, and this is your octahedral shape, and you can just see on the top, like on a regular pyramid, there's 4 faces, and imagine another pyramid that you just place underneath another four.
Okay, got it.
So yeah, so sure, you get that shape when you have something that's bound to six other ligands, but yeah, it's called octahedral because of the not necessarily because of the number of yeah, because of the number of like the faces, yeah. Slash,
Um,
but yeah.
okay. So yeah, although histone-like proteins have not been identified in bacteria, protein X has been identified as potentially able to serve this role based on its physical properties. Okay.
Okay, so what's that role?
I mean, it's like a place where DNA can be like stored, I guess. Like,
Yeah, it could be a way to condense and expand the DNA.
yeah.
Got it. Okay.
Test the possible role of protein X in DNA compaction. Recombinant protein X was synthesized in bacteria and purified for binding studies with the DNA oligomer. And okay, these studies found that two protein X molecules can bind to each molecule of the double-stranded DNA oligomer. When bound, protein X also increases thermal stability of dsDNA oligomer. Okay. I mean, I was thinking like they might ask about GC stuff. They didn't, but that's something that was going through my head.
Yeah. And let's see. Um, they found that the protein X can bind to the oligomer, right?
Okay.
And like uh because we're trying to like just kind of like similar, I guess, like histone binding the DNA. But
Mhm.
yeah, and then it says that it increases the thermal stability. What does that mean?
I mean, it's kind of like measures the temperature at which 50% of the DNA is separated.
And so
Um, yeah,
what happens like to that like the TM it could be called
yeah.
the
I
temperature
mean,
at which 50% is you know denatured or melted. So that would be proportional to stability or inversely proportional.
uh,
The TM value.
as TM goes up, it becomes less stable. So inversely,
The TM would be like if the y-axis is 50%, the x will be the t.
yeah. Okay.
Right.
So,
So the TM is going to be on the x-axis. So if you have an increase in TM, it's going to shift to the right, which means that you'll need a higher temperature to achieve that same 50% melting.
okay.
In other words, TM is proportional to thermal stability. Okay.
What is the DNA oligomer? Is that like what we were talking about, the histo nucleosomes, or?
Mhm. Well, well in Russia they have a lot of oligarchs.
I know it's like multiple things.
Yeah. Multiple, but not a lot. Like not many. It's not like it's a few. Think of it more so as
Mhm.
so a oligomer is like a DNA oligomer is like a relatively short like piece of DNA that contains a few, nucleotides. So
Okay.
same thing with like oligosaccharide, all of that stuff.
Yeah.
Kind of think of it as an in between like a monomer and a polymer.
To determine the structure of protein X bound to dsDNA oligomer, NMR spectroscopy was conducted in 50 millimolar NaCl in pH 5.0 buffer.
Yeah.
Okay. I mean, NMR spec is like, I highlighted it, it's a buzzword. And then when they give us concentrations and pH, it's going to be asked about probably.
Yeah.
And monomeric protein X. So tertiary structure contains double-stranded beta sheet. So it's like secondary, but like altogether, all the different beta sheets and stuff make the tertiary. Comprised of sheets B1 and B2 that pack against a triple-stranded beta sheet. Comprised of sheets B3, B4, and B5, as well as a C-terminal alpha helix and a motif common in GTF and ATP binding proteins called the P loop.
I just had deja vu. Did we do a passage yesterday that there it said something about mono?
Yes, yes, yes. It
And
did.
I
It did.
asked you, and you said quaternary.
Yes, yes, yes.
Uh,
Yeah, yeah,
but
yeah.
so what? So when they say common in a motif common in these other proteins, they could mean like conserved, like evolutionarily, kind of perhaps. Well, I guess that would be more along the lines of like across different species. But yeah, okay, cool. So like yeah, monomer, no quaternary structure, and then we just have a bunch of these like secondary structures that when you're first reading it, don't think it's super important at first when you first read it. But yeah, okay.
Yeah.
Oh, and then yeah, okay, go.
Only beta sheet residues bind to DNA. One side of the beta sheet is positively charged to bind with the minor groove of the DNA backbone, while some nonpolar residues of the beta sheet form intermolecular attractive forces by making contact with the C and G bases in the minor groove. Linearized structure of protein X's diagram in figure 1.
Okay, so it would DNA backbone should be negative. So
Yeah.
if one side of the beta sheet is positive, then yeah, it would bind. Now the nonpolar residues forming intermolecular attractive forces with C and G, like I can see that happen like in the backbone of the peptide, but not really like the nonpolar part. But so when they're saying the nonpolar residues can have intermolecular attractive forces by making contact with the CNG bases, like a nonpolar molecule shouldn't really be able to have intermolecular forces between like with CNG. I mean, of course, there's van der Waals and all of that, right? And hydrophobic interactions, perhaps, but like, yeah, I don't know. Aside from the backbone, like I don't know how it would bind to CG, but whatever. And then linear. All right, then we have the sequence of protein X with secondary elements indicated in the P loop blocks. Okay, so B beta one, beta two, blah blah, and then the numbers, I guess, are the number. Yeah, that E, I guess, is the 10th uh amino acid there, right? Yeah, I guess that's what that is. And so we have, yeah, these sequences, and then the protein, well, the secondary elements, I guess, or no, the P loop is the thing that's in the box, right?
Yeah.
And okay, and like I'm so like this is the 10th amino acid. I'm pretty sure 1, 2, 3, 4, 5,
Yeah.
8, 9, 10. Yeah. All right. Cool. Yep. All right.
Asks what is the ratio of OH to H in the buffer described in the passage? Okay.
Yeah. Okay.
Buffer is pH of 5. So, okay. Um,
We could eliminate two choices right away.
Yeah, I'm thinking. So I would, okay, so originally I put 10 to the negative second, I think.
Okay.
But I don't know, I'm kind of, I mean, I got it wrong. It's like kind of
So this
not thinking.
pH, is it what? What can you describe it? Like,
I mean, it's logarithmic, it's by 10.
it's a little bit more acidic.
Oh, yes, this pH is more acidic, yeah.
So you should have a higher concentration of protons rather than hydroxyl.
Yes.
So,
Oh, so what you're saying, yeah, eliminate these two. Yes.
yep.
Yeah, yeah, yeah.
So, but you chose C?
I chose B.
Oh, okay, okay. So yeah, let's not do that yet. I just wanted to see if you know. So
Yeah, 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 yeah.
yeah, we're gonna eliminate those. So all right, and now I guess pH of 5 um would mean like, let's say like 1E negative 5 for the H plus, and of course it disappeared and it's back. And then we have 1E negative 9 for the hydroxyl, and the ratio of these going to be 1E negative 9 plus 5, negative 9 plus 5, negative 4. Here you go.
Okay, I completely overthought this question. I thought that like since it was a buffer of pH 5, um I was thinking that like the pH and OH have to like cancel out. Like I thought the pH would be like it would be 3 plus something like 3 plus 7 divided by 2. So it's like 5, you know what I mean? Like yeah, I just whatever, I overthought the question, but okay, that makes sense. Um, this is next.
Technique, selectively bind. So what does it mean selectively?
Like affinity.
Hmm? Oh, sorry. So selectively, because I think we made, like, I don't know if we went over an enzyme that was selective in some, maybe with a different student, but selectively means like protein, if it's selectively to bind, if it's going to selectively bind protein X, it's going to bind protein X to the exception of others.
So,
So okay. Um, which technique to most selectively bind protein X on a column and elute it in a purified form past the crude protein mixture through a porous column matrix. Okay. Protein X, let's see what they said about it. Oh, well, I guess we have this stuff on it, but oh, and then part of it's positively charged or something. Whatever. Let me. Okay, cation exchange resin and dilute protein X with a sodium fluoride gradient, hydrophobic interaction resin, gel filtration beads. that's like size exclusion. Um, and then hydrophobic interactions, cation exchange. But I think they said it was covalently bound DNA oligomer and a loop protein. Loot it. Okay. To bind it, we want. Oh yeah, that'll work because they say that this protein X binds the double-stranded DNA oligomer, right? So that would be like affinity chromatography with the double-stranded DNA oligomer as the like that could be like the stationary phase or whatever. So yeah. Yep. Now I want to see if they gave a I thought it was gonna give us something because I was wondering if like the one like if this meant that protein X is positive, like if one side of this beta sheet is positive, and then wait, well then they say other parts are non-polar, so
Yeah.
that can be confusing because like non-polar is like this, positively charged is like this, so gel filtration beads. Maybe if you read porous column matrix, it can sound like that. So I think that these could be pretty like good choices that are wrong. Um, you know. Yeah, wait, so did you choose D first or did you choose like
I did. Yeah, yeah, yeah. No, I got this right. I just want to hear your reasoning.
got it.
So
Yeah.
selective binding is just affinity chromatography, basically. Like,
Uh
you
that
remember that?
so selective binding is usually going to be in a context that well, in general, it just means that it will bind something. It would preferentially bind something to the with the exception of binding to other. Wait, what am I talking about? It's gonna specifically bind something and not other things. So to say that that's just for affinity chromatography,
Oh, it would be a stretch.
I would say like probably a good way to view that because
Okay.
technically like a cation exchange column, right, can selectively bind things that are, positively charged and stuff. So, but yeah, I guess affinity in this case.
I think here what made A and B wrong is that I kind of realized that like part of the protein is positive and part of it is nonpolar. So
Yeah,
this would only bind positive, this would only bind,
yeah,
nonpolar. This is just like okay, like uh, I crossed this one out. But yeah.
yeah.
Anyways,
I was with you on there.
yeah. Okay. Next is this. What is the equilibrium constant expression for protein X binding to dsDNA, oligomer?
Yep.
So
Mass action type of deal. Uh, well, wait, okay. Protein X. Oh, okay. Hold on. So two protein X bind. Wait, so okay. DNA oligomer, and that two protein X molecules can bind to each molecule of the double-stranded DNA oligomer. So we should have two protein X's and I, I see some of these have like the two as like the subscript, which would and wait, do they have okay, yeah, thanks. Because
yep.
also they have like the thing in parentheses inside of the brackets.
Yeah.
So if it's inside of the brackets, it's a single thing, which makes
Yeah.
Okay, that makes sense. That makes sense because it's gonna bind. Um, well, like I just haven't seen it that way. So, okay, that makes sense then. Yeah. So okay, it's not gonna be. We have two protein X's coming in as a reactant, which means our denominator should have protein X with a superscript of 2. So, well, I guess that rules out everything but B, but let's look at some more stuff. So we don't want any like a 2 like in front of a number, in front of like a concentration,
Why?
because in the law of mass action, we take the coefficients in a regular chemical reaction and we turn that into the exponent
Okay.
for like differential equations like reasons. Same thing with like
Hmm.
y if you had like uh something like x times 2x squared, you put the 2x inside the parentheses, right? In addition to the squaring of it. So like, but yeah, usually you've probably seen me draw it before like this. This is going to be c to the power of c over a to the power of a, b to the power of b, right? Law of
Yeah.
mass action. So that's gonna like hold true for like all of like KQ, KW, KA, all that stuff. Uh, so yeah, so we're going to never have, a coefficient in front of the thing like this, and it will have to be as a superscript, which we see in the denominator for B, and you end up with one thing that, yeah.
Yeah. Why wouldn't the two be in front of like because like the way it would be written is um like would this be here? Like would it be like this if it's in equation form?
Yeah.
We got?
Hmm.
Okay.
Yep, and then you'd get protein X parentheses 2 and then the dsDNA,
Yeah.
and yeah. What's happening to the entropy in this reaction? The one that you wrote.
I mean it's I guess decreasing because becoming more ordered.
And also you were coming from 3 like 2 moles of protein X and then the dsDNA, so 3 moles total to 1 mole total.
Mhm.
It's like NaCl. When you put it in water, it turns in like if you have 1 mole of NaCl, you put it in water, you'll get 1 mole of Na plus and 1 mole of Cl minus. You'll get more products. You'll get double the product, so the entropy would go up.
Okay. God, I was like really back and forth on this one. Um,
Well, you okay? So you were able you knew right off the bat it's not quaternary
yeah.
because you saw a monomer, right?
Yeah.
And now let's think about it, right? A beta pleated sheet is secondary, right? But if you have more than one beta pleated sheet, you have more than one thing that's secondary, which means that it must be a higher level than secondary. But yeah.
Yeah. Okay. Okay.
Normally we'll see um like tertiary structure. Like that's how most proteins end up, uh being because of that, because of what we talked about with entropic penalty and all that stuff. So like unless you have like isolate like a beta pleated or whatever beta pleated sheet from like a protein, like the tertiary structure like will be the kind of default.
So,
Spinach.
you ever seen this word? Non-canonical?
Uh-huh.
What does it mean?
Uh, well, I know it more so in a different context, but canonical is going to mean something that is like generally like, well, something that's like the standard or something like that. Like I don't really know, like in the context that I'm thinking of, it's like Western canon. It's like a list of these like Plato.
I had a pass on it today. I want to kill myself. Literally. It was in cars. I sent you a screenshot.
Yeah.
Oh my God. But yeah, I know what you're talking about now.
Yeah. So and then also like if you're if there's like whatever TV show or storyline or whatever that they say is canon, it means like it's part of like the actual whatever story or universe that it's part of. Whereas, if it's something that anyway, but yeah, canonical related to like a stand, it's kind of like a standard. Um, so I guess so now applying it to this context, canonical base pair, I guess are like the regular ones, like A binds to T, something like that.
Okay. No,
So I looked it up. It's just the standard, yeah. So that's what canon is.
this is crazy though. Like I've never seen this in any passage, and I've been through 22 practice exams.
What?
Um,
Canonical base?
like yeah, like
Oh yeah.
it's just I don't know. Whatever. They're trying to be like
They are.
all,
They are. They are. They are.
I don't know how to
It's
word it, but you know what I mean.
yeah, yeah.
Like they're polylinkers and non-canonicals.
Hmm.
Um,
Yeah. And yeah, that primitive
Spermatocytes and the whatever, yeah, whatever.
yeah,
Um,
primitivity of free space and then colony forming units, which I still have to do. And there's yeah, this is a yeah, they're doing something here to because and then another thing is that okay, for the longest time I would always tell my students to like memorize like constants. And then I had my students not memorize constants because a lot of times they give it to you, but there's there's been problems that I noticed from the section bank that require equations that you are not given. Like the volumetric expansion equation, and then the one that we talked about at the beginning of this session, like required you to know that like the charge of an electron, the energy of an electron, the energy like uh with the 1.6 times 10 to the negative 19 stuff. So yeah, they're going for it here. All right,
yeah,
so this is something that seems a bit more um
normal, I guess. Yeah,
yeah.
I don't know.
Let me see though.
I'll be right back. Okay, one second.
Uh-huh.
Okay.
I mean, so this is a weak reducing agent.
We can go through the passage, by the way. Like just so you know,
Okay.
like there's like more than one question I have here.
Okay.
Yeah.
See, compound 1 millimolar can undergo a 2-enzyme catalytic cascade biosynthesis to produce fusaric acid, compound 6, a fungal natural product that plays an important role in plant pathology. The pyridoxal phosphate, PLP, dependent enzyme FUB7 catalyzes the loss of CH3CO2 to form compound 2. So that's what's getting lost, I guess, not what's getting added.
Mhm.
CH3CO2 is that perhaps something. I know, like, okay, whatever. Let's see. So the okay, compound 4 was obtained after the second FUB7 catalyzed reaction with compound 3. So this time they're adding compound 3 to which is an aldehyde, and it seems like it opens up the ring again. Um, the structure elucidation of compound 5 was supported by mass spec. Okay. When deuterium, like water, instead of regular water, it was used in step 3. Step 3, we have, we keep going like to making rings, unmaking rings,
Mhm.
rings. This one, it seems like the nitrogen is part of the ring. And there's like a dehydration synthesis, I guess. Uh, okay. Um, yeah. Compound, oh yeah. Different mass. So if they deuterate it, they have a different mass, so they can kind of tell them apart probably. And then let's look below. Compound 3 was produced from a two-step enzymatic reaction between compound 8 and FUB8, followed by FUB6. The steady state kinetics of the FUB8 catalyzed step, figure 2, are shown in table 1 with several substrates. So we see this carboxylic acid, FUB8 turns it into this uh, aldehyde, which means that we are reducing it, right?
Mhm.
So this is a redox, okay. Steady state kinetics of the FUB8 catalyzed reaction of compound 7 through 10. Um, okay, that's just the arg. Okay, so alkene can give you like this Km value, this Kcat value. We seem then to just extend. We're all right, we extend it, and both these values go, well, wait, Km doesn't change, but Kcat goes down. And then we make it even longer, and both go down. Well, wait, Km goes down, but now Kcat goes up. Then we have this triple bond thing where we have the highest Km and like the second highest Kcat. Okay. Which compound is formed instead of compound 2 if the NABH4 is also added to step 1, shown in figure 1. So that reduces things, but it's a weak reducing agent. It can't reduce carboxylic acids. It can't reduce amides. Um, it can reduce like whatever, aldehydes and ketones and perhaps, yeah, I think also alcohol, yeah, alcohols maybe. Well, let's see. Can't even tell. Oh, okay. So this one gets this entire thing removed. Um, which won't happen because the carboxylic acid is not NADH4 is too weak to reduce that. So getting rid of that. And then we have positive here, positive here.
Thinking D.
What's up?
Would it be D?
D. So in D, I see we lose this double bond and this double bond and this charge. But I would think that a reducing agent. Okay, so I mean, okay, I see a couple of things change for D. For C, I see just that, like, this double bond went there, and then this double bond went here. Everything else seems to be the same, and that could be possible because of resonance, but we want to see what would, like produce an actual change. Um, so so I don't think it's this, I don't think it's this. And then in B, the only thing that changes is we have lost a double bond here. And D, what we have that's changed is we lose a double bond here and here, and we lose the charge of the nitrogen. So yeah, based on that, but not based on anything else, would I guess I lean towards B. But yeah, I mean, what we should be like seeing is okay. Iminium ion. Because I know there's imines and stuff that
Yeah.
we were gonna ask much about, but um, that is a carbon. It's essentially like a carbonyl with a nitrogen carbon, like double bonded to a nitrogen that is also bound to some other carbons. That's an iminium ion, and it can
Yeah,
probably.
I don't have. I only have anatomy and imine.
Uh-huh, yeah. So the iminium is just the amine, but with that positive charge, that additional bond. Just
Oh,
like,
okay.
yeah, just like ammonia and ammonium, the ium
Hmm.
indicates the whatever, the charge positively charged one.
The question is, why doesn't it remove the double bond? That's the thing. Like, why isn't this double bond removed? I thought it'd be reduced.
So there's two double bonds here, right?
Yeah.
And that was like what I was saying, like for like the difference between D and B, because B, you just have the like we're losing this double bond only, right?
Yeah.
And then D, I think, had two double bonds that were lost.
Hmm.
So, you know, if we're going to be reducing something, we're going to be, uh, you know, taking a double bond and turning it into a single bond, like, in that first step of like oxidation, the reverse of it. So yeah, B has a loss of one double bond, and D, I believe, has a loss of two, and it shouldn't, if you had two equivalents, maybe, but yeah, it shouldn't remove both, right?
Okay. I don't fully understand it, but so what you're saying is it targets the double bond on the nitrogen first, but if there was another equivalent, it would target the double bond.
Uh, yeah. Um, in that like generalized biochem redox pathway that I showed you, like, where you have alkane oxidizes to an alkene, alkene oxidizes to an alcohol, alcohol oxidizes into a ketone or aldehyde, aldehyde oxidizes to the carboxylic acid, and then that's oxidation. The reverse is reduction. So reduction can, turn a aldehyde into an alcohol, uh, and alcohol into a double bond, and a double bond into a single bond.
Okay, I just need to remember then that LAH and NABH4 cannot reduce double bonds,
In what?
and they can't reduce isolated double bonds.
Wait, they could.
Really? Chat just told me they can't,
Oh, let me see what they.
and some online forum also said the same thing.
Let me see exactly.
Um, yeah, yeah, yeah. So this is what they said. Um,
Reduce isolated. Well, I'm not sure what you mean when you say isolate. Oh, isolated double bonds in alkenes. Selectively reduces the carbonyl. Does not reduce isolated CT double bonds. Mild. Okay, and then that one. We'll go down a bit. All right, that doesn't do it either. Okay.
and this is what some organic chemistry forum said. That
Um, Now they're able to, okay. Now, okay. So it's because of something else. Um, it can soft nucleophile reacts with the enal after this reaction. Simple. Okay. Okay, so yeah, apparently it's through a different mechanism. So yeah, so what I said about redox, you know, does not only applies. And that's like what I was looking for at first too, like if we're gonna get rid of the carboxylic acid or something. But yeah, reducing agents like the lithium aluminum hydride and sodium borohydride is gonna just work on things that have the carbonyl groups. So yeah, you the NABH4 can reduce aldehydes and ketones, whereas the lithium aluminum hydride can reduce aldehydes, ketones, and carboxylic acid and their derivatives like amides and stuff. Um, but they do not reduce like alkenes.
Okay.
Yeah, it's like a different reaction because they will reduce won't reduce it, but they will get rid of the double bond.
Um, okay, yeah, this is next.
Okay. Going from compound 5 to compound 6. Compound 5 is this. Compound 6 is this. How many electrons are transferred? So 5 to 6. Yeah, we are losing hydrogens. So this should be redox then. So we're reducing. So like my drawing thing kind of disappeared, but if you could hit that annotate.
Oh, so annoying. Yeah, I got you.
Okay, wait, it was right there. So yeah, initially it has like this carbon's bound to two hydrogens, and then here it's bound to one hydrogen. We have a loss of hydrogens, which happens when you have oxidation. And when you have oxidation, you lose electrons. So I would say, okay, I would say it's going to be electrons that are lost. And now is it going to be two or is it going to be four? We remove two hydrogens. We add two double bonds. Double bond is between double bond. Each double bond, addition of a double bond is going to be two. Yeah, it'll be two electron. Wait. All right. Each double bond should have two electrons, I believe.
Okay.
Yeah, because if we have like carbon with one, two, three, four, and we have, let's get rid of that one. So this is oxygen. So okay, so carbon has four electrons and it makes a double bond. Oxygen gains two. In carbon, it's attached to two. So I think each double bond will be two electrons.
So
Because
would
they
you say we gain, we lose?
Mhm.
So like we lose four?
Yeah.
Okay, because I thought that we gain electrons.
Oh yeah. So when you have an alkene like this, and you oxidize it, you'll get this. So you have the loss of two hydrogens in this oxidation, which would also mean, since it's oxidation, that you're having a loss of electrons. So yeah, so that's how I was able to determine that electrons will be lost in order to form these double bonds. Um,
Yeah, I need to look at your the oxidation thing.
yeah, yeah, this could also help. So in a carbonyl, um, in this carbonyl double bond, oxygen is gaining two electrons, and carbon is gaining two electrons. Or I guess I should say they're sharing two.
Mhm.
Carbon sharing two. Let's say this one and this one are carbon, and then this one and this one are from the oxygen. So for each double bond, you're going to have uh, two valence electrons share with whatever you're making a double bond with. And it's also why, like in Huckel's rule, it's like the number of pi electrons. You'll have like two for each double bond. Yeah.
So like would you say like each hydrogen contributes two electrons? Or I mean, hold up. Each hydrogen contributes one electron?
That each hydrogen should be, so like a hydrogen here with one electron can bond with one electron of the carbon. So that'll be one electron. Um, and that'll be true, like, even if this was like a CH3, like if it's so basically if it's a single bond, so each bond requires an electron, like let's say here from the carbon and then here from this carbon. But ultimately, if you think about it in terms of how many electrons are shared, I think that can make it the most simple. So that would mean that a uh, a single bond is going to be sharing, like each thing involved in a single bond will be sharing one electron.
Okay.
If for each thing in a double bond, each one will be sharing two. Sorry, they'll be sharing two electrons.
Yes, that's what I'm saying. Like if one hydrogen contributes one electron then.
Yeah.
Okay.
Mhm.
Okay, I don't want to go real fast for this.
Okay.
And um this is more so just my struggles with mass spectrometry.
Oh yeah. Okay. Molar mass of CAM after its reaction with one equivalent of compound one, and I guess it's that one, and what, 60 oh, CAM on its own is 16,621.
Mhm.
And then this is cam plus compound 1, you get something here and here. Maybe so Mike, okay, this is cam on its own. This should be compound 1 on its own. And my guess is this is the cam after, these two interact, right?
So, but how do you know that it's that? Like, how do you know the one on the right is compound one?
Oh, well, I know that if this was compound 1, like your cam should be between like compound 1 and cam without compound 1, right?
Why?
Oh,
What is the why, Shane? What is the why?
um, okay, I mean, like, I'm just doing this based on what I see, so let me take a closer look here. So, we have cam as our receptor that contain, okay, binding, okay, causes conformational changes, whatever, and wait, several, okay, binding calcium conformational changes exposes hydrophobic pockets. Several methionine residues can be modified by compound 1. These protein modifications can be detected by mass spec scans at Z. The charge, I guess, normalized to +1, figure 2. Thus, the numbers next to the peaks correspond to molar masses. Um, Prior to compound 1 labeling, CAM is treated with EDTA, followed by desalting in order to prepare the protein for calcium-dependent labeling with compound 1, mass spec analysis of CAM, and the products of its reaction with compound 1 in the absence or presence of calcium ion. So we know CAM on its own is this. And then we have something with CAM and compound 1, and then CAM with compound 1 and calcium ions. Okay. Yeah, the only thing I can think of is just that we know CAM will be the 16,621. And when we add compound 2, we have 2 new peaks. And so one of them has to be the peak of compound 1, and the other one should be the peak of CAM in the presence of compound 1 compared to by itself. So either this is compound 1, which would make this CAM in the presence of compound 1, and I feel like if they're saying that it reacts with compound 1, like compound 1 isn't the thing that's changing, but cam is the thing that's changing. And since we know that the leftmost is cam on its own, it would make sense that cam in the presence of compound one would be closer to the original cam. I think that's how I'm thinking of it. Um, but molar mass, I mean, did they say anything in the passage like that can help or methionine,
No.
blah blah blah, compound one. Oh, so we have cam, we add compound one, we get compound two, and well, I guess they're not asking about compound two, but
See what the explanation says.
okay. Addition of 96 grams per mole. Yeah.
Oh, wait,
So
wait,
it's
what?
compound two, I believe.
Where did they give us 96? Wait, like, wait, like, we actually have to add, like, get the, so we have to calculate the molar mass then?
Let's see. So,
Okay, that makes sense though.
uh-huh. So it would just be for this, right? That's what you're adding.
Hmm.
The whatever, this thing. So, um, so yeah, I think that it would be required then, right? So,
Okay, well, that makes more sense because I thought they just wanted us to infer, like, from the graph without anything else.
yeah,
Um,
what I always say, like whenever someone tells me, "Hey, the answer is just here,"
mhm.
I'm like, "Nah, it's probably in the passage."
Yeah. I mean, it wasn't directly in the passage to play devil's advocate, but like
So,
we had to really infer that from this thing.
well, so like if you didn't, so like from what saw is just the bottom all the way down. So I didn't know anything about what cam looks like,
Yeah, true, true, true.
but here we could see that cam is this thing, RS, and when we add compound one, we get this added to it.
Yeah.
Then you just do the math there. But you know, you're telling me to like look just at here, and it's much harder to do that.
Hmm.
So, but yeah, whenever someone tells me, "Hey, not you don't have to read the passage for this; it's just here," like I know it's usually not true.
Yeah. So,
Um,
I don't know if you want to maybe skim through the passage. This is also like the only question I have from this passage, but
mhm. Got it. All right, these are all spectrographic techniques, and they're talking about oh, some of these we don't see that often, like this or this. Okay. Table one, role of these residues in this GABA receptor binding site. Okay. Seems like okay that we have in table one the residues and the role of the residues in the GABA binding site and the oh wait, the residues aren't like just amino acids. It seems like they're different like secondary structures like alpha helices, beta pleated sheets and stuff.
So yeah, circular dichroism, it looks at secondary structure.
Got it.
Now, I don't know the answer. I would guess it's this, but what I also wanted to make sure that you know is like what I was thinking. Like UV spectroscopy, I usually think of aromatic stuff. And so it spoke about aromatic side chains, and that's what I ended up putting. I put C. So,
Um, got it. So I know for UV they test for conjugation. So, and I guess that, and we see with the pi interactions that could make sense also. Um, and okay, so we're not creating fragments and separating them based on mass. So B can be out and ultraviolet. The only thing that I could think of in terms of X-ray crystallography is like that's how we know the structure of DNA, like the DNA structure. And
oh, okay.
this is telling us that we know things about secondary structures. I guess that would constitute a structure then. So I think that could work. Um, yeah, I know math spec won't work. Ultraviolet, I could see how that could be tempting. Circular dichroism, I didn't remember what that was, but you did, so good job. Um, non-covalent interactions between ligand and receptor.
Interesting. Okay. Well, I didn't really know what X-ray crystallography was, but like, I mean, all these were tempting except B, honestly, because it talks about alpha and beta sheets. Circular, it says it's secondary structure.
Yep.
Um, but I guess X-ray crystallography determines specific non-covalent interactions. Okay. We go to on B.
Uh, so yeah, so X-ray crystallography is a way to get a three-dimensional molecular structure from a crystal. So if you're making an Anki card, uh, that could be something that you can add. And so since we're looking for a tertiary structure, which is a 3D structure, then it would make sense to use X-ray crystallography.
Mhm.
Because yeah, I'm pretty sure that's how we know like the structure of DNA. I think Mary Curie or someone like that, like
Mhm.
that, and then but she died, and Watson and Crick got the credit, something like that.
Yeah, yeah, yeah.
X-ray
Um,
crystallography, a technique where X-rays are used to study the structure of crystals. Oh, it was Rosalind Franklin.
okay.
I'm
Yeah.
putting all the female scientists together in my head, and that's probably like some type of gender thing tested in the whatever,
Yeah.
like social section.
No, no, okay, yeah. Those are like the main two though. Yeah, I think like for DNA, I think of those.
Yeah,
Okay. X-ray. X-ray crystallography provides a high resolution tertiary structure and allows researchers to see. Yeah, so we need to know we can also see interactions between ligand and receptor.
yeah. So I would just say three-dimensional, and
Yeah, three-dimensional.
tertiary like happens to be three-dimensional, so that works. But if you say just tertiary, then it it seems like it would not include other things that are 3D. But yeah, to get a three-dimensional, you know, uh structure of a crystal, I guess, of a solid. Um, yeah.
Oh. Um,
Then
and
circular.
then yeah, suck. This was the last problem I want to go over.
Um, okay. Okay, they should have double the content of DNA. So, like, otherwise, normally you would have four haploid sperm, but now you'll still have wait, you're still gonna have four, but the genetic content of each is going to be doubled. You're not gonna like tetraploid is like if it's one cell that has four times the genetic content, and we know that's not gonna happen because the other steps of meiosis proceeded normally. So we should not have, eight. Or sorry, we shouldn't have one tetraploid and we shouldn't have eight anything. We should still have four. It's just that they're going to just have double the amount of DNA. So I think it's going to be four diploid.
Why wouldn't it be eight haploid?
Because everything else is happening normally, right? So when you have your like cytokinesis and they split like one into two in meiosis one, and then they have meiosis two where each of those two split again to get four, right? Like this, and then that.
Mhm.
My this is meiosis one, this is meiosis two. So you're still since everything else is working properly, right? You're still going to end up with four, right?
Yeah.
It's just that the only thing that's different is that the DNA got doubled twice. Because anytime you have meiosis or mitosis, which means you're taking one cell and you're dividing it into two, you need to double the DNA before that so that each uh, daughter cell has a copy. Like if you just had one, DNA strand here, like, and you make two like cells, like this one DNA strand is going to be, one going to one cell, the other going to the other cell. So that's why they need to double the content before that uh in the S phase. So yeah, so we should have four like ending cells because that's what happens in meiosis, like after meiosis one and two. Just like mitosis would give you two cells from one, meiosis is just doing that twice essentially. So from one cell you get two, and then from those two cells you get four. And the only thing that's different is that chromosomal duplication happened twice. So yeah, we should just get four diploid sperm.
Mhm.
Yeah. So chromosomal duplication happened twice, but all other steps happen normally. If all the other steps occur normally, then it'll produce four sperm. But since replication happened twice, each sperm will have twice the normal amount of DNA, hence four diploid sperm.
Oh,
Mhm.
that's really it.
Okay.
Is there anything you like recommend people to do like a week out from their exam? Um, just practicing, I guess.
Oh, yeah, I guess you can like go through like the Jack Weston like cheat sheet or the other cheat sheet stuff that I have and just kind of like glance over them and kind of like use that to kind of like indicate to you like, okay, this is something that could be on the test. This could be something that they're testing on. Like I would like maybe just like look over that a little bit each day and like maybe, familiarize yourself a little bit more with the stuff that you're less familiar with. Um, so it seems like you have a pretty good grasp on the content. So I would also say that like I mean, like for the some of the cars passages that you sent, like, we don't have to spend a lot of time on it, like, on some other day, but I want to go over like some of them, like for I'm reading it right now, canonical text. But like
Yeah.
for instance, right? Like, because I remember that passage, like what I would say for the main idea for that passage would be the that today or at the lower levels, grammar is the reason that so at the higher levels or at the lower levels, since the goal is to achieve like basic literacy, they use books that are relatively easy because of that goal. But if you are at the higher levels of education, you read canon so that you not just have a basic literacy, but you have this new like kind of like sophisticated kind of like cultured kind of thing, which I guess pretty much what you have. So yeah, I'll just take a look at these. I know that there was like I think one of them that it was the one that was about like the printing press and all that stuff. And you wrote
Yeah.
like social leads to tech. Um, but I would say it's more so that it's this combination of things that are not necessarily because the passage talked about social determinism and technological determinism. Social determinism means social changes caused this evolution of literature or technology. But the author was neither type of determinist, but thinks that it's like this in between middle ground. So I'll just like send you like an email where I would just like kind of like adjust some of the main ideas. But yeah, I would say yeah, like to yeah, look over like the cheat sheet at content and see like, what type of content you feel, not the best about. And then uh what are you like doing for cars like as you practice like day to day?
I do 4 pages a day. I mean, sorry, passages
Yeah,
a
yeah,
day.
yeah. Yeah. Okay. Okay. And so yeah, since most of the maps that I saw or main ideas that you wrote are really good, um, I would maybe look at the type, see if you find any type of pattern in the types of questions that you get wrong for cars. Like, is
Yeah.
it going to be like a weakener question? Is it going to be a main idea question? Is it going to be like, how is this word used in the passage? Yeah, something like that. So yeah, I would say continue doing cars. Try to find a pattern in the types of questions that you're getting wrong. Glance over the cheat sheet, like, every day, to kind of like just refamiliarize yourself with stuff. Um, and maybe even like look more into some of those topics that could showed up on like the section banks. I'm thinking of like stuff about plasmids. I'm thinking of things like meiosis and mitosis, like just brushing up on those, Ankiing them, I guess. Uh, but yeah, those are just the things I'm thinking of.
Hold
Yeah.
on. Do you just wait? Do you know what this is?
Oh, this equation?
Yeah.
It looks like, I mean, there's some like ideal gas constant in it, and then there's partial pressures of things or ion concentrations or something. Maybe this is like the uh movement of ions. Or no, that's could be a voltage then. Maybe it's a voltage between like the, you know, the membrane potential or something like that.
Okay. I was just wondering because I watched this like YouTube video of a guy going through like all these like just like reviewing this sheet,
Yep.
and this was on it, and I was like, what? Apparently, it's derived from the nurse equation,
Yeah.
but
Got it.
yeah, I mean, it just seemed very like
Uh-huh.
crazy, but
Got it. Got it. Okay. All right. Yeah. So I'll look into that. But
okay.
yeah. But
And one last thing, like,
yeah.
I'm just wondering, like the day before, do you usually recommend students to study or no? But like,
Now that's on the week of, like, you're, I would say, pretty much done with doing any problems or questions.
really?
I would just do like a passive, like Anki is fine. Or like, just a passive, like kind of glancing through the cheat sheets like I said, like today. Um and yeah, just like uh making sure that you go to bed like super like early, because people just like they always have a hard time falling asleep the night before. But yeah, I would say that last week to basically use to like kind of like recuperate, in a sense, like to so that when it's test day, like you're completely ready, like energy wise. You're not like, oh my God, this again. I just did like 8 passages yesterday. So yeah, I would say just like passive review. And we could probably go over like some of those like questions from my website. 'Cause I know that you did those and we didn't really like go over them, but those that could be like a nice like end of, end of your prep type of thing to do.
Yeah. There are like a couple of things that like I have like an insane document where I any like concept I don't know I write it there. So I'm gonna like be going through those just like super random. Like one bullet point's like archaea, another is like Henry's Law, you
Yeah.
know? And like stuff I don't fully understand from watching videos or reading, I'll also bring to our sessions next week. But okay. Yeah, I was actually gonna speed run through Section Make Volume 1 next week. So I guess that's not
So
the greatest idea. And like not study Thursday, but
got it.
okay.
Yeah,
Okay.
if you do that, I would just say to do it like before, like let's like by at least like the 19th, like to stop doing like questions and stuff.
Understood. Okay. Okay.
Awesome. So yeah,
Um,
see you yep tomorrow and
tomorrow.
enjoy your dinner.
Thank you. Thank you.
It's going to be different from what you have been having, but
Yes. Yes.
all right. Yeah.
All right. Wait. What was the total?
Oh yeah. Uh 132.
Okay.
That's
Thank you.
gonna be your score. All right. Take care.
Hopefully.